Hi, I am Sanjay Patel. Today, in this lecture, we are going to discuss three important rings, rather important types of rings, and then we'll see some examples of different types of rings. Okay, so first of all, let us begin with the first definition of special type of ring, which is very important. My first definition is definition of what is called integral domain. So this is a very important class of ring, integral domain. So the definition, let R plus dot be a commutative, let R plus dot be a commutative ring with unity. Be a commutative ring with unity. If the ring R has no zero divisors, if the ring R has no zero divisors, then R is said to be an integral domain. Is said to be an integral domain. We have already defined what is the meaning of zero divisors. We'll quickly recall, and let me write this in a different way so that you can understand what to check if you want to prove that a ring is a integral domain. So I can say a ring R plus dot is said to be an integral domain, is said to be an integral domain if first condition R is commutative. That means multiplication of any two elements in any order is taken gives the same result. That is, A into B is equal to B into A for every AB belongs to R. Secondly, R has the unity element. Okay, and the third condition is the ring R has no zero divisors. R has no zero divisors. So if you want to prove that a given ring is an integral domain, then you must prove these three conditions. It is commutative, it has unity element, that is multiplicative identity, and it has no zero divisors. Let us recall the definition of zero divisors, what we have understood in our previous videos. If R is a ring, and if you have a non-zero element A in the ring R, then this non-zero element is said to be a zero divisor of the ring, is said to be a zero divisor if there exists another non-zero element B in R such that A into B is equal to 0. In short, if product of two non-zero elements is a zero element, then the two elements are called zero divisors. We know if A is a zero divisor, then the element B is also a zero divisor. Okay, that means if this is satisfied, if A not equal to 0, B not equal to 0, if you have two non-zero elements, but still the product is 0. Okay, if this implies if A into B is 0, then A and B are called zero divisors. Okay, but remember, to prove a ring is an integral domain, it should not have any zero divisors. I mean, this condition does not hold. That means this condition is not true. So that means if you want to prove that a ring has no zero divisors, R has no zero divisors, then what you must prove, this is very important thing, R has no zero divisors, if and only if, just prove that for any two non-zero elements, if A and B are two non-zero elements in the ring, then their product is also non-zero. Okay, means product of two non-zero elements in the ring, if it is also non-zero, then the ring has no zero divisors. This must be true for all A and B belongs to R. And this can be proved equivalently as that if AB equal to 0, then we must have either A equal to 0 or B equal to 0, because here this comma means and, this means and. So if A is not equal to 0 and B is not equal to 0 implies AB is not 0 for all A and B belongs to R, then the ring R has no zero divisors. Same way or equivalently, you can prove that if product of two non-zero elements or rather product of two elements is 0, then at least one of the element, either A is 0 or B is 0, must hold for all A and B. So this is a very, very important thing that you must remember. This is very, very important condition to show that a ring has no zero divisors. A ring has no zero divisors. So this is a very useful condition to show ring has no zero divisors. For example, in the ring Z6 plus 6 dot 6, okay, in the ring Z6 plus 6 dot 6, if I take two elements, say A is equal to class 2 and B is equal to class 3 belongs to Z6, then A dot B, okay, A dot B, that means class 2 and this dot is the multiplication modulo 6. So dot 6 class 3, this product is class 6, 2 3 is 6 and 6 modulo 6 is 0. So we'll get product of 2 and 3 0. And note that this 2 is not 0 and 3 is also not 0, because in Z6 the 0 element is nothing but the class 0. Okay, this is the 0 element. So even though we have two non-zero elements 2 and 3 in Z6, that product is 0. So these 2 and 3 are 0 divisors. That means the ring Z6 has 0 divisors. So Z6 is not an integral domain. Z6 is not an integral domain. We know that Z6 is a commutative ring. It has a unity element also, but it has 0 divisors. So it is not a integral domain. On the other hand, if I take the example of the ring say Z phi, comma plus phi, comma dot phi, if I consider this ring, then in this ring, the elements of this ring are say class 0, class 1, class 2, 3 and class 4. Now if you take any two non-zero elements, say 2 and 3 are non-zero, and if you multiply here, say 2 is not 0 and 3 is also not 0, okay, and we have 2 into 3, that is 6, and 6 is equal to class 1 in Z phi, 6 congruent to 1 modulo phi, so that is not 0. So your product of two non-zero elements is non-zero, and that you can check for every pair of elements. So in Z phi, you can show that for every A and B belongs to Z phi, for every A and B belongs to Z phi, if A and B are not 0, then the product A into B is also not 0. That means the ring Z phi has no zero divisors. We know that Z phi is a commutative ring. Whether you multiply any two elements in any order, you will get the same result. So it is a commutative ring. It has a unity element. This is the unity element of this ring. And also Z phi has no zero divisors. Z phi has no zero divisors. So what can we say from our definition? From the definition, we can say that this Z phi is an integral domain. Z phi, comma plus phi, comma dot phi, this is an integral domain. So in integral domain, I will write short form as ID always. Okay. So this is the understanding of the definition of integral domain. A commutative ring with unity in which there is no zero divisors, which has no zero divisors, is called an integral domain. A very, very important type of ring. Another important class of rings we want to consider as a definition of second ring, as definition of what is called division ring. It is called division ring, and the other name of this ring is skew filled. It is also known as skew filled. Okay, so I write the definition like this: let R plus dot be a ring with unity. Let R plus dot be a ring with unity. Just note that I am not considering the commutative property here. That ring need not be commutative. That means A into B need not be equal to B into A in this ring. So R is a ring simple, and it has a unity element. Unity must exist. That is the important thing. If every non-zero element, that is important, every non-zero element in R has a multiplicative inverse. If every non-zero element in R has multiplicative inverse, in other words, every non-zero element in R is a unit element, This way also we can define. If every non-zero element in R has a multiplicative inverse in R, then R is said to be a division ring. Is said to be a division ring, or it is also called a skew filled or skew filled. Okay, so every non-zero element in R has multiplicative inverse. That means inverse element for the operation of multiplication must exist. Okay, so this condition you can understand in a symbolic way is that for every A belongs to R, and if A is not equal to 0, then there exists, say, B belongs to R such that A into B is equal to 1 is equal to B into A. Then you know that this B is called multiplicative inverse of A. Or in other words, we can also say that A is a unit element of the ring. So if every non-zero element is a unit in the ring, then it is called division ring. Okay. At the same time, I want to consider another and the last type of ring in this lecture, and then we'll take examples of all this kind of rings. So my next definition is another very, very important class of rings. It is known as a famous thing, say, filled. So filled is a special class of ring. Okay. So let me write this way. A commutative division ring, is called a field. A commutative division ring is called a field. Okay, we know what is division ring. We have just defined. It is a ring with unity. So it is a ring means it satisfies all the 8 axioms of the ring definition. It has a unity element, that is the 9th condition. Every non-zero element has multiplicative inverse. That is the 10th condition. Okay, so it is a field means it satisfies all these conditions, and it is commutative in addition. So A into B is equal to B into A. So it satisfies all the 11 properties. Okay, one can describe field in a detailed way by writing all the 11 conditions. So 8 conditions of ring. One condition is unity element, that is 9th condition. Then 10th condition is commutative property. Okay, and 11th condition is multiplicative inverse must exist. Okay. So we can also define ring, rather a field, in this way. Definition of field in a different form, that commutative ring, this will be easier to understand. A commutative ring with unity element, in which every non-zero element has multiplicative inverse, or you can say every non-zero element is a unit element of the ring. Okay, then, or rather let me write not R. Every non-zero element has multiplicative inverse in the ring. Then it is called a field. So let me write this way. A commutative ring with unity in which every non-zero element has multiplicative inverse in the ring is called a field. So this is our definition of field. Okay. One simple example, I will just mention that Z phi, the ring Z phi comma plus phi comma dot phi, this ring is a field. This is an example of a field, because we know that Z phi comma plus phi comma dot phi, we have already mentioned that it is a ring. This is a ring. Okay. We also have seen that Z phi has no zero divisors. It is an integral domain. It has a unity element. So the unity element in this ring is class 1. You know what is Z phi? Z phi has 5 elements. Class 0, class 1 up to class 4. It has 5 elements. So this is unity element. Okay. Then class A dot phi, class B is same as class B dot phi, class A. That means multiplication is commutative. So it is a commutative ring. So this Z phi is commutative ring. Okay. It is a ring. It has unity element. It has commutative ring, and every non-zero element in Z phi has inverse. So let us discuss that. Every non-zero element in Z phi has inverse. Non-zero means other than 0. We should not take this. Just we have to check whether the elements 1, 2, 3 and 4 has multiplicative inverse or not. So for example, let me take say the element class 2. And what is the inverse, multiplicative inverse of class 2? So what you have to check is this. Class 2 dot. Dot means the multiplication operation. The multiplication operation here is dot phi. So class 2 dot what? What class I should write here so that I will get the unity element. That means I get class 1. So class 2 into something must be equal to class 1. Then I can say that this class 2 has multiplicative inverse, or it is a unit element of the ring. So that you can check by putting one by one all the elements from Z phi other than 0. So if I put 1, 2 into 1 is 2. So it is not equal to 1. 2 into 2, 4. Okay, let me write like this. 2 dot 2 is equal to 4. Okay, and 4 is not equal to 1. Then if I put 6, then 2 dot, sorry, if I put 3 next element, say there is 3 also. So 2 dot 3 is 6, and 6 is congruent to 1 modulo 5. We are in the ring Z phi, so we have to divide this result by 5, and whatever the remainder we get, that we are writing here. So this 1 we are getting in this case, that means 2 into 3 is equal to 1, unity element. This is unity element. Okay, and since it is commutative ring, 2 into 3 is 1 and 3 into 2 is also 1. So I can put 3 here. That means 2 inverse. 2 inverse is class 3. That we have proved. And we know that if A inverse is B, then B inverse is also A. So immediately I can write 3 inverse is 2. Okay, so no need to check for the next element. So what I have done, I have taken only 2 and 3. Now let us check for 1. What is the inverse of 1? If I take 1 inverse, it is the identity element. So 1 inverse is 1 because class 1 is the unity element, which is the identity element for multiplication. So 1 into 1 is always 1. Okay, so 1 inverse is always 1 in every ring if it exists. And finally, what is left is the last member of the ring Z5, that is class 4. My question is, what is the multiplicative inverse of 4? So what should I find is 4.5 dash is equal to class 1. What should I keep in place of this blank? Okay, so that you can put one by one. So 4 into 2, 4 into 1 is 4, 4 into 2 is 8. If I put class 2 here, then 4 into class 2 is 8 and 8 is equal to 3. So it is also not 1. So I cannot put 2 also. If I put say 3, 4 is 12 and 12 is equal to 2 in Z5. So that is also not equal to 1. So 2 is also not an inverse of 4. If I put 3, 4 is 12, then if I put 4 itself, if I keep 4 here, yes, then it satisfies the condition. So let me write this way. 4 into 4, 4 for the 16 and 16 is congruent to 1 modulo 5. So 16 is equal to 1. So 4 inverse is 4 itself. Thus we have proved that every non-zero element in this ring Z5 has inverse. 1 inverse is 1, 2 inverse is 3, 3 inverse is 2 and 4 is a self-inverse. Okay. So as a conclusion, I can say that Z5 is a field. It is a commutative ring with unity in which every non-zero element has multiplicative inverse. Okay, these examples are just to explain that what is the meaning of the field or integral domain, like that. Let us make a list of all the rings and check all the properties. So let me prepare a table for this. I will put here somewhere. Yes. Okay. Okay. So what I am going to do here is, okay, it is too large. Let me make it small so that we can understand everything at a time. Yes. Okay. So now let me put the title here. This is a problem number, or say just a serial number. Then I will write which ring I am taking here. Okay, or the set rather, not the ring. What I will write is the set R and the operations plus and dot, and then I will write here whether this is a ring or not, then it is an integral domain or not, okay, and it is say division ring or not, okay, and finally it is filled or not. So this is a very important table. So let us start with the first and simple one. The first example, that the set of natural numbers with the operation of addition and multiplication, it is not a ring, so no need to think about all these things. But before I take further, let us recall all the definitions. You know what is an integral domain? A commutative ring with unity in which there is no zero divisors, or a commutative ring with unity without zero divisors is called an integral domain. Division ring, a ring with unity in which every element is a unit element, or every element has multiplicative inverse. Every non-zero element has a multiplicative inverse. Filled, a commutative ring with unity in which every non-zero element has multiplicative inverse. And second example is Z plus dot. means a ring, a set of integers with respect to usual addition and multiplication. It is a ring. Okay. Is it an integral domain? What is a set Z? Set of integers. If we take any two integers, if they are non-zero, then product is also not equal to 0. We know that product of two non-zero integers is always non-zero. For example, 3 is not 0, 4 is not 0. 3 into 4 is 12 and 12 is also not 0. That way it is true for all the integers. So it is an integral domain. It is a ring with unity and it is commutative ring and has no zero divisors. And is it a division ring? What is the condition for division ring? It has a unity element and every non-zero element must have inverse. But it is not a division ring, because if I take some elements, say 2 inverse, then 2 inverse does not exist in this ring. So it is not a division ring. Just let me not write here, or rather let me make this table little more smaller so that I can explain something. Okay. Okay. Now let me make this table smaller. Okay, fine. Now, just to explain that this is not a division ring, for the second problem, we know that 2 belongs to Z, but 2 has no multiplicative inverse. 2 into something is equal to 1 is true if I put 1 by 2 here, and 1 by 2 is not a member of Z. So 2 has no inverse. So it is not a division ring. And since 2 has no multiplicative inverse, it is not also a field. So Z is not a field. The third example is, say Q, R and C, all these falls in the same category, all have the same answer. It is a ring, it is an integral domain because product of two non-zero real numbers or product of two non-zero complex numbers is always non-zero. Okay, so it is an integral domain because it is a commutative ring with unity, and every non-zero complex number or every non-zero real number has multiplicative inverse. So it is a division ring also, and it is also filled. Okay. Then the next example I want to take is the set of say the set R is equal to the set 2Z with respect to operation of this simple addition and multiplication of integers. We have already proved that it is a ring. Okay. And since it is a subset of the ring of integers, here it contains only integers, and we know that product of integers, product of two non-zero integers is always non-zero. So in 2Z, if you take any two even integers which are not zero, then product is also an even integer which is not zero. So this is an integral domain. Yes? No, it is not an integral domain. Why? What is missing? Unity element is missing. Yes, unity element does not belong to 2Z. So this ring is not an integral domain. It has no zero divisors, that is fine, but it is not an integral domain because unity does not exist. Unity does not exist. This does not exist. Okay. Since it is not it does not have unity element, it cannot be division ring and it cannot be field also, because in division ring and field definition, it must have unity element. So no need to check anything else. Next, let us check the ring of matrices, say 2 cross 2. I am taking R is equal to M 2 cross 2, set of all 2 cross 2 matrices, and plus and dot means matrix addition, and this is matrix multiplication. Okay. For this operation, we know that it is a ring. We have proved it. Is it an integral domain? What do you say? Means what you have to check is only two things. R is a ring, we know. Can I say R is a commutative ring? No, because product of two matrices, okay, is not always commutative. You cannot get A into B is always equal to B into A. So this is not an integral domain. On the other hand, you can also say it has zero divisors. The ring of matrices has zero divisors. You can find two matrices, say 1, 0, 0, 0. This is one matrix. Another matrix is say 0, 0, say 1, 0. Then product of these two non-zero matrices, this is not zero, this is not zero. But if you find the multiplication, that will be a zero matrix. So I can say R has zero divisors. So it is not an integral domain. And since it has no zero divisors, it is not commutative also. If it is not commutative, it is not a field. It is not a field. Okay. And is it a division ring? Is it a division ring? Can I say that every non-zero matrix has multiplicative inverse? No. You know very well, every non-zero matrix cannot have its inverse. Inverse exists for a matrix which is square matrix only if its determinant is not zero. Let us take the same example what I mentioned here. This example 1 0 0 0 is a non-zero matrix. This is a non-zero matrix, right? Because mod of because all elements are not zero. But what is mod of A? Mod of A is 0. So this is a singular matrix. Its inverse does not exist. So every non-zero matrix need not have inverse. Therefore, it is not a division ring and it is also not a field. Fine. Let us take another example. Say if I take Z6 plus 6 dot 6, this, and 7, I take Z5 plus 5 and dot 5. We know that Zn is always a ring for any value of n, where n belongs to capital N, means n is a natural number. So it is a ring in both the cases. Is it an integral domain? The example number 6, Z6 is integral domain? No. Because we know that class 2 is not 0 and class 3 is also not 0. But class 2 into class 3 is 6 and 6 is equal to 0. So that means the ring of residue class is modulo 6. That is the ring Z6 has 0 divisors. Therefore, it is not an integral domain. Okay. Again, every element in Z6 does not have inverse. So it is not a division ring also. You can verify that 2 has no inverse in Z6. Same way, since it is not a division ring, it is not a field. Okay. And finally, Z5, which is very important class of rings. So that, very important example of ring. It is a ring. It is an integral domain. And it is a division ring. We have already seen in this example above that every element in Z5 has inverse. This is the example in which I have mentioned that all the elements has multiplicative inverse. It is a ring. It has unity element. It is commutative. So we already solved this problem, and we know that Z5 is division ring. It is also a field. Okay. Remember, by definition of field and division ring, I can say every field is always a division ring. If R is a field, implies R is always a division ring. But the converse of this is not true. Means if R is a division ring, it need not be a field. We will be discussing the example of this type later on. Let me go further about another important example of ring, in that is Q root 2, the set of all real numbers of the form A plus B root 2. We have also proved this thing in detail, that the set Q root 2 with the operations of addition and multiplication of real numbers is a ring. It has unity element, and also it has no zero divisors, because it is a subset of R and R has no zero divisors. So any subset of R also cannot have zero divisors. Similarly, it is a division ring because every non-zero element in Q root 2, we have found that its multiplicative inverse exists. We have discussed this in our previous videos. So that you can check, and it is also filled. So this satisfies everything. Another important class of example, that is Zi, Gaussian ring. If you remember, what is Zi? Zi is the set of all complex numbers of the form a plus ib, where a and b both are in Z. A and b are integers. Okay. And what we have put about this example, it is a ring. Okay, we have discussed this problem in detail in our previous videos. So just recall, it is a ring. Is it an integral domain? If you take two non-zero, see, Zi is nothing but set of complex numbers, and set of complex numbers has no zero divisors, because you know that if you take two non-zero complex numbers, its product is always non-zero. So if you take any two non-zero Gaussian integers or any two non-zero elements in Zi, then its product is also non-zero. So it is an integral domain. It has a unity element as well. 1 plus 0i is the unity of this ring. It is also a division ring. Yes? No. It is not a division ring. Every non-zero element in Zi has not necessarily a multiplicative inverse. Why? If you remember, or you just go through the previous videos and you will see, we have proved that the only elements of the ring Zi which has multiplicative inverse are 1, minus 1, I and minus I. Means these are the only 4 units of the ring Zi. So this is not true. It is not a division ring. And since every non-zero element does not necessarily have multiplicative inverse, it means it is not a field also. Okay. So this is another important thing. So we have discussed all these important examples, and further I want to write 2 more problems as the next thing. So let me extend this. Say, directly, independently. Consider the 2 special rings which I want to discuss here. One is the ring, the ring of matrices of the form Z, W, then say minus W bar and Z bar. This Z and W belongs to C, set of complex numbers. This with respect to addition and multiplication of matrices, we know that it is a ring. This example of ring we have mentioned in our previous say lectures, and gave you to verify all the conditions of ring. So it is a ring. It has a unity element also. Unity exists in this ring. What is the unity element? It is the identity matrix 1 0 0 1. Okay, it is an identity element 1 0 0 1. It is a unity element, and we know it is not commutative. Okay, it is not commutative ring. So R is not an integral domain. R is not an integral domain. Okay, and since it is not an integral domain, because it is not a commutative ring, it has also no zero divisors, because it is a ring of matrices. You can find 2 non-zero matrix, or you can find a matrix whose multiplicative inverse does not exist. So R is not a field also. Is not a field. Yes? No. This is not true. Let me change this. It is not an integral domain, is fine. But R is a division ring. This is an important example. R plus dot is a division ring. Means every non-zero element has multiplicative inverse. We have also proved that R means if you take any element here in this, any element A, Z, W, minus W bar and Z bar, Z bar, okay, this is non-zero, then A inverse, which is equal to say 1 upon determinant of A into adjoint of A, this always exists. This always exists. So for every non-zero matrix in the ring R, this ring has inverse. So it is a division ring. But it is not a field because A into B, let me write here, therefore R, yes, we have written already, it is a division ring, but A into B is not equal to B into A, okay, in R. That is, R is not commutative ring. R is not a commutative ring. So it is very, very important example. R is not a commutative ring. Means what I want to say here is, this is an example, the ring of matrices of this form where these elements are the complex numbers in this form. This ring is an example of a division ring which is not a field. Every field is always a division ring, but converse is not true. So this is division ring. It is a division ring, okay, but not a field. Okay. Another important example I want to mention, and you can verify that there is set R, the ring of quaternion rings, that is A plus I into B plus C into J. Let me write this way, not IB. I will write B into I so that it looks better. A plus BI plus CJ plus DK, where all A, B, C, D are real numbers, they are real numbers, and I into J, okay, is equal to 0, okay, is equal to J into K is equal to, say, K into I. And also we know that I square is equal to -1, J square is equal to -1, and K square is equal to -1. Another thing we note is Ij is equal to, say, Ij is equal to minus Ji, we can say minus Ji. So it is not a commutative ring also. Okay. So this is an example, another example of a ring which is a division ring. You can verify it is a division ring, okay, but not a field, So we have two examples of rings which are division rings but not a field. We have already proved this for this example of a ring of quaternion, that every non-zero element has multiplicative inverse, but it is not commutative. Ij is not equal to Ji. Okay, I into J is K, but J into I is minus K. So they are not equal. So it is not a commutative ring. Okay, so we have listed all these important examples of ring, and that you must remember, which are useful in our say further theory of rings. And in the next lecture, I am going to discuss some important theorems about say rings and integral domains and field. So till then, goodbye. Thank you.